In this video, we would like to learn how to take the very first steps in hypothesis testing, and that would be how to determine the null and alternative hypothesis in real-life scenarios. Please note, in the examples that will be considered, we will be painting the pictures of real-life scenarios and how you might go about testing hypotheses based on the status quo and what we suspect might be happening now. And in order to really get a full grasp of this, I always encourage my students to pay more than usual attention as you get into applied inferential statistics. So, the first example here says that an appliance manufacturer stockpiles washers and dryers in a large warehouse for shipment to retail stores. Sometimes in handling them, the appliances get damaged. Even though the damage may be minor, the company must sell those machines at drastically reduced prices. The company goal, unsurprisingly, is to keep the level of damaged machines below 2%. One day, an inspector randomly checks 60 washers and finds that 5 of them have scratches or dents. Is this strong enough evidence that the warehouse is already failing to meet the company goal? What do you think? Is a single instance of checking 60 washers and finding 5 of them having scratches or dents? Take note, 5 out of 60 represents 0.08333, about 8.3%. So, do you think this 8.3% is significantly greater than this 2% for us to conclude that we already have evidence that we are no longer meeting the company goal to keep the level of damaged machines below 2%? As a statistics student, how would you go about this? The first step is to identify the population of interest. The population here will be the population of all washers or all machines that are stored in this large warehouse for shipment to retail stores. The next question is, what characteristic of this population are we interested in this scenario? That will be our parameter of interest. And as I sense, it will be the percentage of machines that are damaged. So to write that, the parameter of interest, P, will be the percentage or the proportion of damaged machines out of all machines stockpiled in a large warehouse. So the next question is, do we think this is strong enough evidence that the warehouse is failing to meet the company goal to keep the level of damaged machines below 2%? To test an appropriate hypothesis and state conclusions based on the available sample data, what are the null and the alternative hypotheses? In order to find the null and the alternative hypothesis as requested by the question, the first step is to note that the null hypothesis is usually the hypothesis of the status quo. That would be the hypothesis that documents or makes a statement of what is already existing or what is assumed to be existing. Before the inspector randomly checked the 60 washers, the goal is to keep the proportion or the percentage below 2%. So that would be the assumed state of things or the status quo. So the null hypothesis is represented by H with a subscript 0, and it is, in this case, the fact that the proportion or the assumption that the proportion is kept below 2%. Well, in the case of the null hypothesis, we always include equal to. So take note, it could be 2% or below. This is a common practice. So please note, the null hypothesis must always have the equal to sign. It must never be in the alternative. So that leads us to then the alternative hypothesis. This is the research or test hypothesis. This is represented by different notations. Some people use H subscript 1, some people use H subscript A, some people use H capital A. And in this case, it will be the opposite of the null hypothesis. If this is less than or equal to 2%, this will be the alternative, which is the proportion greater than 2%. For the purpose of our class, and to keep things consistently easy and simple, we are going to adopt H1 as the placeholder for the alternative hypothesis. So we are going to write this as what we want to test. We want to test if the proportion is now greater than 2%. So with that said, we proceed to the next example on how to write or correctly set up the null and alternative hypothesis. In this example, we're told that in a clinical trial, 26 out of 852 patients taking a prescription drug daily complained of flu-like symptoms. Suppose that it is known that 2.8% of patients taking competing drugs complain of flu-like symptoms. What is the parameter of interest? We're interested in the population of patients who are taking what? Drugs and who complain of flu-like symptoms. The parameter of interest would be this percentage of those patients. So in this case, the parameter of interest again is P. So the P, the parameter of interest, represents the percentage or the proportion of patients taking prescription drug daily who complained of flu-like symptoms. The next question, or the next part of the question, is there sufficient evidence to conclude that what we know before, which is 2.8%, that more than 2.8% of these drugs users experience flu-like symptoms as a side effect? So this is what we want to test. This is our research hypothesis. So in other words, I have information pertaining to my alternative hypothesis. I would like to test if P, the proportion, is more than 2.8%. This is what we want to test. Always remember, what goes in the alternative hypothesis is the statement that we want to test. So now that we have the alternative hypothesis, I can go back to the null hypothesis. That will be the opposite. Of course, it must have equal to 2.8%. Then, if I choose, this is same as equal to, and for some other people, this is also equivalent to P less than or equal to 2.8%. For our class, we will simply adopt the equal to here. So, please note that in this case, since there was an immediate statement of what was going to be tested, that was the first thing I wrote. And then I simply wrote the equality symbol or the statement of equality in the null hypothesis. So we proceed to the next example. In this example, we learn that Kellogg's makes many food products, including a variety of breakfast cereals. At the company's Battle Creek, Michigan plant, frosted mini wheats are produced and packaged for distribution around the world. If the packaging process is working properly, the average or mean fill per box is 16 ounces. This is definitely the status quo. That is, what should be. Okay, we read further. Suppose every hour, quality analysts at the plant select a random sample of filled boxes and measure their contents. They do not wish to unnecessarily stop the packaging process, since doing so can be quite costly. Thus, the packaging process will not be stopped unless there is enough evidence or sufficient evidence that the average fill is different from 16 ounces. So this would be what we would like to test if we're already having that case. Because if it's already been different from 16 ounces, we definitely want to stop the process. So in this case, what is the parameter of interest? The characteristic of interest with regard to the population of frosted mini wheats would be the average fill per box. So in this case, this is about average, the mean, mu. That is the average or mean fill per box of frosted mini wheats. Then the next part of the question says we should state the hypothesis that reflects the status quo. What reflects the status quo is always the null hypothesis. Under usual circumstances, if there has been no change, what will be? What will be is that the average, the mean, will be equal to 16 ounces. It will be 16 ounces. That would be the status quo. That is the null hypothesis. Then the alternative then would be what we want to test. What we want to test at any point in time would be if the average is different from 16. Take note, if this is a number line and this is the number 16, different from 16 means it could be greater or it could be lesser. So this leads us to average not equal to 16 ounces because this takes care of it could be greater or it could be lesser. We will be back here to talk about how many tails this test has. But before then, let us look at the next example. In this next example, we are told that an issue that faces individuals investing for retirement is allocating assets among different investment choices. Suppose a study conducted 10 years ago showed that 65% of investors preferred stocks to real estate as an investment. In a recent random sample of 900 investors, 360 preferred real estate to stocks, which means the remaining 540 preferred stocks to real estate in this example. What is the parameter of interest? Our interest here is about a percentage who prefer stocks to real estate. So P, the parameter of interest, will be the proportion or percentage of investors who preferred stocks to real estate as an investment. Then we move further. Are these new data sufficient? Where is that new data coming from? They took a random sample of 900 investors, and while 360 preferred real estate to stocks, we conclude that the remaining 560 preferred stocks to real estate. So data here that we have just collected, are these new data sufficient to allow you to conclude that the proportion of investors preferring stocks to real estate has declined from 10 years ago? This is what we want to test. We want to test if the proportion P has declined or reduced or become smaller from what it used to be, which was 65%. So what it used to be, the null hypothesis, would be P equals 65%, which is the same as 65 divided by 100, or 0.65. And then the alternative is to check or to test whether it has declined or become lesser than the formerly existing 65%. This would be our alternative hypothesis. At this point, before we move any further, it is important to learn something that is going to be very crucial later on, and that is the number of tails that this test has. So let's start with the last example. Whenever you are asked how many tails does a test have, only go, strictly speaking, to the alternative hypothesis. I'm not going to waste your time. Simply go to the alternative hypothesis and look at the sign here. This says the percentage could be less than 0.65. That means it only goes in one direction. So this is a left or one-tailed test. Then let's see the next example. For the number of tails that this test has, this is saying the mean is not equal to 16. That means it could be greater, it could be lesser. So this is 1, 2. this is a both or two tailed test. Let's write this well. My pen appears to be acting up. So a both or two-tailed test. And then for the one earlier, in this case, if you look at the alternative hypothesis, this is only going in one direction, that P is greater than 2.8%. So this is a one or right-tailed test. It is going in the right tail. And for the one up here, what do you think? Is it one-tailed? Is it two-tailed? Is it left? Is it right? Or both-tailed test? I would argue that this is greater than, is going in only one direction. So this is a one or right-tailed test. So with that, we will see more of this as we progress later on. Now, having answered the question of what type of tail test it is, let us proceed back to the next page, and that would be page number 5. Here I have a documentation of the steps in the hypothesis testing process. Well, I do not see much value in reading through all of this to you. You're welcome to refer to it as your reference point when you get mixed up about what step you are. So, I would prefer to use examples to drive the process of teaching you what the steps involve. So far, this is what we have covered. We have covered how to set up the null hypothesis and the alternative hypothesis. This piece we have covered, and we're still going to see some more examples on that on the next page. So, more practice on correctly writing the null hypothesis, which is the statement of the status quo, and the alternative or research hypothesis. In this example, we are told that Nexium is a drug that can be used to reduce the acid produced by the body and heal damage to the esophagus due to acid reflux. The manufacturer of Nexium claims that more than 94% of patients taking Nexium are healed within 8 weeks. I would like to emphasize something quickly here. This is a manufacturer making a claim. Whenever you make a claim in statistics, we need to test it. And that hypothesis or that claim you're making is going to be our alternative hypothesis. It's always that statement we want to test to see if sample data backs it up or not. So we continue. In clinical trials, 213 of 224 patients suffering from acid reflux disease were healed after 8 weeks. Write both the null and alternative hypotheses below. Well, the null, the alternative. Personally, I would prefer to write the test hypothesis immediately since I already know what it is. And that is to note that I'm interested in percentages. So P, percentages. And I'm interested in that percentage being more than 94%. So greater than 0.94. 94% is 94 divided by 100, which is 0.94. So with that said, if this is greater than, I will set this guy as equal to 0.94. So that is this. That is that. I have written both the null and the alternative hypothesis in this case. What you quickly observe is that whenever I have the alternative hypothesis given or the statement given of what I want to test, I simply serve it to the alternative hypothesis. We proceed to the next example. A certain brand of apple juice is supposed to have 64 ounces of juice. When I hear supposed to have, that is telling me what the status quo should be. So already, I do, in this example, have the null hypothesis. But I'm not going to write yet. Because the penalty for underfilling bottles is severe, the target mean amount of juice is 64.05 ounces. So this is about the mean. So I'm going to write mu, mu. However, the filling machine is not precise and the exact amount of juice varies from bottle to bottle. The quality control manager wishes to verify that the average, the mean amount of juice in each bottle is 64.05 ounces so that she can be sure that the machine is not over or under filling. Write both the null and the alternative hypotheses below. Well, I have a statement of what should be, that is the status quo. It is supposed to be, the average is supposed to be 64 ounces. Well, in this case, we're interested in verifying whether the machine is not over or under filling. Over would be greater than, under would be lesser than 64 ounces. So this would be the case of not equal to 64 ounces. So take note that in this case, we want to test if we are missing that point, which is 64 ounces, and that would mean we should set it to not equal to. Not equal to takes care of both of this, because if it is not 64, it could be greater or it could be lesser. So again, in this case, we see another example of how to set up your hypothesis correctly. Then, this is very important because if the hypothesis is set up wrongly, every other step afterwards is wrong. So that is why we're taking sufficient time on this part. Then the next example. Price and Associates is a residential home developer in the Phoenix, Arizona area. They build single-family homes in the 300,000 to 500,000 price range. Because of the volume of homes they build, they have refined their processes to be very efficient. How is that so? For example, they have a company standard that a home should not require more than 25 days for framing and roofing. Once I read this part, this is already telling me what their standard should be, what their existing status quo should be. So this is already giving me a hint that in the null hypothesis, the average amount of time they are going to use should not be more than 25 days. I'll be back to that. Let me read the question to the end. The managing partner at Price and Associates wishes to test whether the mean framing, the mean framing and roofing time has changed since the mean time of 25 days was established a few years ago. Write both the null and alternative hypothesis below. Well, for my null, I have a question I have a statement here that immediately tells me what was existing or what should be existing. And that would be not more than 25. Not more than 25 would be, not more than 25 would be either equal to 25, and 25 being the ceiling or the greatest number, it means you can only go lower. And the only change that we can test then will be mean greater than 25. For the purpose of our class, take note that this statement is equivalent to null mu equals 25 in statistical hypothesis testing. That is okay. All right, then we have another example. In today's economy, university students often work many hours to pay for the high cost of a college education. Suppose a university in the Midwest is considering changing its class schedule to accommodate students working long hours. The registrar has stated a change is needed because the mean number of hours worked by undergrad students at the university is less than 20 per week. Immediately I spot somebody making a claim. I already know this claim needs to be tested as to whether it is true or false. And whatever needs to be tested needs to go to the alternative hypothesis, which is to check if the mean number of hours is less than 20 hours per week. That needs to be checked. So that definitely is what is going to the alternative hypothesis. So if that is going to the alternative hypothesis, then the null hypothesis will be mu equal to 20. This is the same as the null hypothesis, mu less than or equal to 20. As long as the test hypothesis or the alternative hypothesis has already taken strictly less than. With these examples covered, I hope we recall that in this case, this would be a one or left-tailed test. Why? Because the direction of the inequality here is in only one direction, which is going left. This would be a both or two-tailed test. You'll see how this will become very useful soon. And this would be a right or one-tailed test. Right one-tailed test. All right, with that, we can say that in this case too, you have a right one-tailed test. And with that said, all of this helps us to learn how to set up the correct hypothesis test in hypothesis testing.